Welcome back to the second half of Daniel's session, and so I'll let him take it away.
All right, let me just try to get this full screen again. Awesome. Yeah, thanks, Aditya, and thank you very much for continuing this. I know this is a lecture with a lot of entropy, right? So hopefully you were able to decompress as well and make all of these a bit lighter. The second part is a bit more aggressive because we're going to be talking about robustness and something called attacks. So I hope you're not discouraged by the fact that we have a lot of entropy in this talk, but we're going to continue on this idea of uncertainty, robustness, and understanding why is it important for scientific machine learning that we're talking about uncertainty and robustness. And again, going back to this problem, right? It's very interesting why these two images are different. And I think I like to start this point with something a bit far away from the things that we talk about. So robustness to noise and attacks, robust generalization, and active learning strategies. But thinking about something from the fields of arcs, there's this very famous image from René Magritte called the treachery of images. And he talks about it in an interview about the famous pipe. This is not a pipe, but the particular famous pipe. He was greatly criticized by the fact that he said, this is not a pipe, but could you stuff this pipe? And if not, it's just a representation. And if he had written in this picture, this is actually a pipe, that's also a lie. So what is the point of really talking about whether this is a pipe or not? Well, if you think about machine learning, basically everything we're trying to do is some sort of representation. We're trying to learn what is the intrinsic meaning of this, and what does it really mean for us to assign a scientific insight to any data. It doesn't have to be an image. It doesn't have to be an image of a pipe. That's not a pipe. It could be any kind of data point that we're interested in. How is this different, really, from the things that we do? Isn't machine learning pretty good about already looking at the treachery of representations? Let's say you have a very, very simple function to be learned, say 2x plus 1 over here, and you even add a little bit of noise to that particular function. Just say over here, have a standard deviation and a particular Gaussian noise that you're going to add to this function. There's a corrupted function, y tilde over here, and you're going to get a linear model to this. So if you actually do this experiment, and you're going to see that the error against the true data is going to decrease as you increase the number of data points. So isn't this some sort of robustness against the actual problems, underlying problems, the treachery of images in this case? Well, turns out that neural networks are very, very finicky. And it has been discovered that, no, they're not necessarily robust to these things in a lot of different examples. One of the classical examples is called adversarial attacks. So let's say you have an image classifier, again, going back to the space of everything that we talked about and starting off these concepts. This image can be classified as something like a panda, and I think it's pretty reasonable that as a panda, I would assign a higher confidence to this panda above like 57%, but that's okay. The image classifier detects this as a panda quite correctly. Now, one of the interesting outcomes that was discovered back in 2013 was that it could add a little bit of noise to this particular image and get something that's essentially, to a human eye, identical to the first image. But that noise is constructed in such a way that this final image is classified with 99% confidence into a given. Now, to me and to you, all of this image and this image are indistinguishable. However, to a model, this tiny amount of noise was enough to completely change the result of the classification. And this is not by a small margin of classification. This is 99.3% of class probability, as we discussed before. So this is not a good example of a well-performed uncertainty quantification. This is something else that's going on. And so to this example, researchers called this an adversarial attack. So let's say that you have you're trying to confuse a certain classifier, an image classifier. Look at a self-driving car, and then you add a couple of stickers in your stop sign. Don't do that, please. Let me just put the legal disclaimers. Don't do that, and you could just do that hypothetically. But if you did that, you could as well just confuse these image classifiers in your self-driving car and have this stop sign be recognized as something completely different. And that is an immense peril to all of the security, the safety of all of these methods. You could have people wearing weird clothes, and these people were not identified by an image segmentation model. And you can run over these people if you do that kind of thing. And there is an infinite number of examples in which fairness and safety of AI comes into play, and that is also likely in the case of scientific applications. Another example, this is a very interesting video that was created in 2018 and shown in ICML, one in which researchers painted, 3D printed and painted this turtle with these patterns of noise and confused the classifier to identify this as a rifle instead of a turtle. So imagine this at large scale security applications. This is a silly example, of course, but imagine this, but in the other side. Imagine that you had a rifle and you try to conceal it by converting or attacking your image classifier. This is exactly not what you want to do, of course, right? And this is exactly what we're trying to avoid in scientific applications. So in very high stakes scenarios, what you really want to do is you want to avoid problems such as adversarial attacks. This is one example of lack of robustness of neural network models. And what we want is really to try to optimize robustness. Let's say this is one example that was performed back where I worked with Lawrence Livermore. Is a simulation that used 268 million atoms, which is a ridiculously large number of atoms. This tries to simulate the formation of materials, in this case, tantalum, at very large scales. So running one of these simulations takes so much supercomputing power that you can start measuring the value of these simulations in tens of thousands to almost hundreds of thousands of dollars. And so you don't want to mess up one of such simulations, right? So if you do that, what you end up doing is you can look at, say, a system that's like this. And of course, we're going to skip the physics. What happens here is that all of these green lines represent the mechanisms of dislocations of really how materials deform. And you can try to understand what really happens at the atomistic scale with the materials that have been deformed. And you can only do that because you look at systems at very, very large scales. So the question is, if my models are not robust and it takes them the tiniest amount of noise to actually give me the wrong answer, am I confident enough that my models are going to be able to simulate hundreds of millions of atoms and spend hundreds of thousands of dollars perhaps in supercomputing resources at production? I am particularly not entirely confident that's the case. And so how can we improve these models for deployment in these very large scientific applications? So a simplified math to go back to this example and to understand it in the context of this lecture, we want to understand a little bit of the math. You can try to think about adversarial attacks as something like, let's try to have a classifier. This is a typical loss of a classifier. You have predictions, you have a soft plus, and you classify these labels. And your objective in a classifier is this, right? You're trying to find a set of parameters theta that minimize this particular loss, which can be a cross-entropy loss in a traditional classifier. The adversarial loss, that tiniest amount of noise, is not a random noise. Here's the difference between just adding random noise from that particular first example that I showed and the adversarial attack. This is a noise that really maximizes for your misclassification loss. So you see over here that h of theta is basically your model. You have your model making a prediction over a certain input data point x, and you added a small perturbation delta. An adversarial attack, therefore, is something that really takes in this loss, applies to the original image a certain tiny perturbation. And this tiny perturbation creates enough confusion in a certain model at the same time that it really does not make the perturbation indistinguishable from the original. And that's really what this loss is doing for us. So it is not just a random noise. It's not really a process of sampling arbitrary points around the space of image and trying to misclassify them. No, it's a targeted attack. And that's why it's called adversarial attack. You want to purposefully make force your model to make a misclassification. And that's the interesting part. You see that before, what we had is a problem of minimization. And here you have a problem of maximization. So mathematicians in the room will probably recognize this kind of min-max problem as being something very tricky to also perform. But it is really what can be done in order to prevent us from these adversarial attacks. So let's say that instead of training a model just with a typical cross entropy loss, we train our model in such a way that we're finding the weights of a neural network that minimize, and that's the first part that says over here, a loss function that's a perturbed loss function, not anymore just the typical cross entropy loss. It's a loss function that takes into account all the possible data points under study and all the possible perturbations that are possible, all the possible perturbations that are allowed for this set that you define. And this is what this maximal over here tells us. It tells us that for each cycle, for each epoch, for each evaluation of your model, you're also going to evaluate it against possible adversarial attacks. And this is the interesting part about defending your model. You see, you're not anymore just evaluating your model according to just a pure cross entropy loss. You're incurring into an additional cost that you're multiplying the number of training evaluations that you have to do by a significant amount. Just because at each evaluation, you're going to have to add an additional perturbation, adversarial perturbation to your input data in order to try to confuse your model as much as possible. So think about like a goalkeeper who's training to get a ball, and every single point you're going to introduce some sort of variation in that goalkeeper in such a way that you're going to force that particular goalkeeper, the particular player, in really not only finding out the patterns of the one who's shooting the ball, but also the patterns that he or she is using in trying to confuse you in really shooting that ball. So this is exactly the kind of understanding that we have in terms of adversarial attacks in machine learning. And it's very interesting. You can take this loss function and you can actually train machine learning models using that. Let's do the same kind of experiment again. And this is one of the examples shown in ICLR 2019, in which you take the original image is classified as a primate over here, and this one classified as a bird. So we can do the traditional adversarial attack strategy, in which now this is a dog and this is a turtle, and it doesn't make sense. The perturbation is very tiny. You can see, even given the resolution of this image, that there is some slight perturbation to here, but maybe not here. What happens if I train a model that's somewhat robust, and I try to make the tiniest perturbation that I can to this image to classify it as a dog in a robust model? This is what you get. This is a very interesting result in the case of neural networks, that you can see that this image, this small perturbation that you have to apply in order to convert this image from a primate into a dog, is actually interpretable, right? You can see that the original face of this monkey over here became the nose of the dog, and you have a couple of eyes over here that come from like the feet and the origin. If you convert this bird into a cat, you can see even the ears of the cat over here, the striped pattern of the cat. So it's really interesting because somehow by imposing adversarial attacks and these adversarial training, we're capturing the semantics of what it means to be a dog or a cat beyond just those filters, but also with their perturbations. So we're no longer able to just make tiniest perturbations and create your model with these lack of robustness using these methods, but indeed can just misclassify them.
So when you're training like with these perturbations, is your model only robust against like the specific perturbation method they use, or does it generalize against like all perturbations?
That's a great question. So you see over here that we have an L2 trained at the top, right? And that is because we trained our model to be robust against perturbations in L2 using L2 norm. That's not necessarily the case in all examples. You have this space delta, right? Delta is the set of all perturbations you're allowed to make in your image in order to make that interpretable. Let's say these two images are fairly similar. So it means that the tiniest perturbation, small delta, that you apply from this to transform into this is actually pretty small. And so the subset of capital delta of allowed perturbations is actually much smaller than this, right? The norm of this perturbation is much larger. And by increasing the norm of the perturbation, it means that it becomes harder and harder for you to confuse the model with the tiniest perturbation. And perhaps that's exactly what we want. Like, we don't want that turtle from the video to be recognized as a rifle just by painting small dots in the chart. We actually want something more robust than that. So yes, not all perturbations, we're not defending a model against all perturbations. We're defending them against specific perturbations that we defined beforehand. And one of the challenges of the field, and I think there's a lot of people who might be interested in working in that area here in this community, is that how do you defend a model against all possible perturbations? And is there any way for us to generalize beyond this idea of small perturbations? Because in a sense, that's what humans do, right? We're pretty good about capturing really this ideal Platonic representation of stuff, like Platonic representation of a monkey or of a bird and a cat or a dog. We can recognize the essence of it somehow. And somehow, neural network models are not there yet. So how do we make them actually achieve that kind of understanding of the actual physical reality? So I think this is why we end up connecting back this process of robustness into science plus AI, right? Because science is the process of really understanding and figuring out the truth behind things. And perhaps going to that process of understanding what is the truth passes along the idea of robustness. Any other question for now?
So like in this case, when you're describing the L2 norm, is this L2 norm from like in the original space of, let's say, these pixels, or is this in like some representation?
No, this is from the pixel space. Yeah, so L2 norm of the perturbation in the image space. Okay, so these are all very, very important questions. And it really makes us understand why this happens, or at least that this process can be at least fairly interpretable, but they're not limited to images, right? Like recent examples, this is a very, very interesting paper in which researchers were able to find adversarial examples in LLMs. You can actually ask an LLM to generate a step-by-step plan to kill tiger and a giant appendix to that particular prompt. And that particular appendix ends up being an adversarial example that allows us to kind of jailbreak the safety railguards of these LLMs, especially in the chatbots that you have access to online. So another very important issue of safety that here is enclosed by the same concept of adversarial attack. This is not a small perturbation, granted, right? It's a pretty big perturbation, but assume Claude stall against after Atlas tutorial manuscript is not exactly an interpretable small perturbation, but it's enough for us to access models in ways that they shouldn't be accessed before. So this is just an example on how adversarial examples end up existing beyond the space of images. How do you explain all of these things? So I wanted to really show you a couple of slides on building intuition on why adversarial examples end up existing. So let's say that you have variational encoders, and it goes back to your question here on whether these distances in adversarial examples can be done in the image space or in the latent space. Let's say that I have both a latent space, for example, one created by a variational encoder, and the image space over here. And I'm just making this example with very, very simple to be didactic here with the MNIST data set between images 0 and 1. What you could do is you can create this particular latent space, and using this latent space that is here, you can verify what are these latent representations of these adversarial examples that you construct for your system. So you can take this classifier, classify it 0 as 1, and create the adversarial examples, encode and decode them, and then look at these distances and displacements that are made in the latent space. So when you do that, what you end up recovering is, say, you have a two-dimensional latent space of this MNIST for this MNIST subset of MNIST, one in which you have zeros and ones, fairly interpretable. I think everyone who has worked with variational encoders and generative models in general has seen some flavor of this, right? And you can create a classification boundary, for example, for taking each one of these images and passing through a classifier that's trained separately, and of course, reconstruct them in terms of adversarial attacks. So the idea is that if you try to confuse a model and perform a adversarial attack on them, you're going to see that each one of these points that were originally one are not pretty far away in this from the decision boundary, right? The surprising thing is the adversarial attack for all of these things is actually not necessarily going towards the decision boundary. In fact, a lot of these movements and these placements of the latent representations, when you perform an adversarial attack, is not perpendicular to the decision boundary that we usually think about, right? And this is a very interesting phenomenon. The decision boundaries here, you have zeros, you have ones, and you have these displacements. And you can see over here the decoded images. Why does this happen? The intriguing part is that it is confined, when you confine yourself to these kinds of visualizations in 2D, it's very difficult to understand why adversarial attacks happen. But if you add an additional dimension to the VAE space, suddenly what you start to see is a decision boundary that's not just like that very well-defined plane anymore. You have these manifolds, a manifold of images that lies in perhaps 2 dimensions over here, and you have these decision boundaries that are not very sharp. In fact, it end up being very curved in a lot of different examples. So the typical picture that we have in terms of classifier is something like this, right? You have one class, another class, and you have a decision boundary over here. But perhaps this is not the best representation for a neural network classifier. So one of the very interesting examples that was proposed by Adi Shamir and co-authors was that images lie in a particular manifold of images, and decision boundaries are not necessarily boundaries in the same manifold. They're not orthogonal to the manifold of images. What you have here is some sort of dimples. You can see over here that the red examples are slightly above the decision boundary, and the blue examples are slightly below the decision boundaries. So they're classified as different things, but the decision boundary is not in this format anymore, separating these classes exactly like this. This ends up being a consequence of these high-dimensional spaces of images. The manifold of image is extremely lower dimensional compared to the all possible examples you could create with, I don't know, 1024 pixels. So because of that, what you end up creating is you train neural networks to make these very low gradient manifolds. And when you create that, the authors call this a dimpled manifold, you end up having these adversarial examples that are easy to construct. You can see that it's very easy to move away from this into an adversarial example just by moving not from this directly in the manifold of images, but towards a decision boundary that's actually super close to your image. And this super close to your image means that it's a tiny perturbation that is created in order to move away from the decision boundary or from the class that you're creating in your system. So in fact, what the authors did when trying to analyze this example is you can perform adversarial attacks on a manifold of images. So constraining your attacks in the same space that generates all of these images. So you can see here an attack that converts a plane in the CIFAR dataset into a bird. So you change the colors, you have a very high norm. So going back to that question of whether the norm is high or not, you have a very high norm compared to what you had before. And maybe this could be a bird in the very low resolution that you have. But if you do an off manifold attack, you can confuse this into a bird, to transform this into a bird with very high class probability and very small modifications to the initial figure. And you can see at this smaller norms for your perturbations. So it's a very simple example, and of course, an intuitive picture, which is why I'm trying to convey it to you on how neural networks don't always behave the way we want it. And the kind of picture and representation of reality that they're capturing, it may not be the same kind of representation of reality that we're capturing when we're looking with your own eyes. So we had a question here.
Yeah, so could you please go back to the previous slide? Yeah, here, so I was trying to visualize between the left scenario and the right scenario. Can I understand? Like probably the left scenario is like on the lower dimension, so like on this plot like 2 dimensions, or like on the plot on the right it's like 3 dimensions, but we also know like intrinsically a neural network like this.
Right. Yeah, so this is in terms of picture, mental picture that we hold and that we use to explain to ourselves why certain phenomena are happening. This here is, I'm just drawing this because this is what we usually think when we talk about classifiers, right? A very well-defined decision boundary. On one side of the decision boundary have one class, and the other side of the decision boundary have another class. And the decision boundary lies more or less in the same manifold of the system. Here, you also have 2 different classes separated by decision boundary. But you see over here, the red dots, the red examples are slightly above the decision boundary. And these blue examples are slightly below that particular decision boundary. The decision boundary is not necessarily making a very sharp gradient in the space, the high dimensional representation space of the images.
Key difference on the right picture is like a higher dimensional space.
Correct. Yeah, which is something expected, right? Which is why this kind of formalism or this kind of discussion is interesting in the concept of robustness of neural networks. By representing things with a very high dimensional space, perhaps we're engaging into these errors. Yeah, so this is just the typical naive textbook representation, but maybe this is something closer to how we should be thinking about these decision boundaries and the consequences that emerge from them. Okay. Any other questions regarding this so far? so far, not so far, but the things that end up happening is that you can find adversarial attacks not only in images and text, but current research that's very interesting tries to find whether even these very powerful methods, such as like AlphaGo and many other systems that try to that certainly outperform humans in the space of, say, playing Go, can actually be susceptible to adversarial attacks. Well, the question is, if we have a superhuman intelligence from a very philosophical sense, wouldn't it be able to outperform humans in every single condition? Well, if that was the hypothesis, then yes, that kind of superhuman ability would be able to outperform humans every single time. However, even these very powerful models that like win over world champions of Go are susceptible to things like adversarial attacks, which is very interesting. You can actually play the game in a very tricky way to force the model here, say the adversary playing in white, to force the model to capture these white pieces here, and then you recapture the whole thing using your white pieces. So it's somewhat a very naive case that a human would not be able to will not be able to fall for, especially a human that is a champion in such games. But somehow during the process of performing reinforcement learning and training these methods, these models to perform well, we haven't achieved this kind of superhuman intelligence. And perhaps this is the kind of thing that we really want to achieve in Science plus AI. So it goes back to the idea of what do we really try to optimize, and what is the kind of mental model that we're bringing out of this? Is really the ability to play Go, or is the ability to win models in certain win humans in certain circumstances in which the games of Go follow the patterns that we expect? And those are different things. And maybe in science we want the first one, but we end up through machine learning getting the latter one. And so that's how we end up thinking about these things. A lot of these artifacts, so to think more broadly on what is really causing this and why models behave like that beyond just the manifold and the classification, you can think about training neural networks as just like some sort of stochastic gradient descent or optimization in the space of a loss function that really drives down a loss and gets a set of parameters that have been optimized, right? And this is the very typical path that we take. And the artifacts, some of the artifacts that show up have a root in this optimization process of neural networks and the losses themselves. And this is why we go to the second part of this second part as well of the entire lecture in terms of robustness. So what is the notion of robust generalization? So that requires us to go back to the idea of losses and loss landscapes and why they're important. So let's say that loss landscapes, especially in neural networks, they're highly non-convex, right? You don't expect a purely convex loss function that you're going to optimize and find a global optimum very easily in neural networks. Instead, actually, we expect the opposite. So let's say that we had a slice of a particular loss function, and you have two parameters, theta 1 and theta 2. So you have a neural network of millions of parameters, and you modify only two of these parameters at a time. And then you plot what is the loss that you incur into as you modify these parameters. For a regressor, we know how to do it. We know exactly what is the loss, and we know exactly how to train. I promise you I would come back to this because this is the process that we train neural networks in the end. But a question that we should ask ourselves is, let's say we look at this particular loss function that we have here on the left, and we have optimized model number 1 and optimized model number 2. And these two models, let's say that they have the same magnitude of loss. So if they have the same magnitude of loss, they have the same expectation value over here. But the question is, are they equivalent? And if they're not equivalent, why they're not equivalent? What is the relationship between model architectures and these loss landscapes themselves? So one of the ideas of inspecting these processes of creating new loss landscapes is to really modify parameters 2 at a time and start plotting these results. So the machine learning literature has been quite prolific in forming these results. You can explain, for example, why some architectural changes in neural networks end up creating loss landscapes that are very chaotic and have a lot of bumps like this one on the left, and how adding skip connections, for example, to ResNet 56 ends up creating much nicer gradients for your system, enhancing trainability. So this is the kind of architectural change that enabled very deep neural networks to be created in the space of image classification that really move away from this very rugged loss landscape and really gets us better models. And so one of the tricks that really enabled us to do deep learning. But beyond that, beyond just the idea of modifying from a chaotic to a well-behaved loss landscape, we might want to think about this visualization of loss landscapes from the model and the parameter perspective. What you really have over here is you optimize a model and then you perturb the weights in order to get different loss functions. So this is exactly what we're doing here. This L of t is a loss landscape that is that has perturbed weights in a certain random direction, right? And these random directions can be 1D, 2D, and so on. With one more trick, which is this trick over here, we just renormalize the layers in order to be compatible with the, say, ReLU, which is scale invariant, and then we can plot and normalize the loss landscape in your systems. And the trick is going back to this one-dimensional plot and trying to correlate it with the generalization power of your neural networks. So a lot of studies have been done on this, and the intuition behind it, which is what I like to convey here, is that if you had the loss function for a training set shown here in black, and if you have a loss function for a testing set that is slightly shifted from your original loss function, that is, there's some slight component of out of distribution there, not exactly, but slight component of out of distribution, and then optimizing your model to get to a flat minimum of your loss landscape ends up creating a smaller generalization error when we move from train to test compared to optimizing model towards sharper loss minima. And so that initial question that I asked you on whether these two models are equivalent or not, the intuition is they're not. And here's why. Because the sharp minima, even if they have smaller losses, they end up creating losses that are smaller in the sense of they're closer to, say, a global optimum, they end up creating higher generalization errors, which is exactly what we do not want in a lot of different examples. Remember, the picture is empirical risk minimization, but we're trying to extrapolate beyond our training set. How do we do that? And this is the kind of explanation that we want. So I'm a very big fan of thermodynamics, and here's some more words on entropy. The idea is that when you think about these things from the perspective of entropy, you can actually think about a average or some sort of smooth average of all your parameters in this sense over here. And as you perform this smooth average, you end up computing, associating each one of these points to a value of entropy. And this value of entropy is in the space of parameters that your model has. So that means higher entropy systems have flatter minima. Lower entropy systems have sharper minima. And that kind of sharpness or flatness of models can be quantified quite easily and quite generally. Just to show that it is general, this has been studied a little bit in machine learning literature, but of course, I'm a molecular simulation person, so I ended up doing it for the case of molecular simulations. So one of the problems in extrapolating molecular simulations is that one that I showed before, molecules exploding, atoms going all over the place, which is not physical. So what we did is we trained a neural network model that quantifies the dynamics of these. Certainly, Zach showed a couple of examples on Monday. Murat also showed a couple of examples this morning in how these models tend to fail sometimes and how much better they can be. And so this is an example of model that was just trained in different number of layers, and we get better performance overall in terms of generalization. In fact, we don't have to optimize the terms of all the hyperparameters in order to see that the model is better or not. We could look instead at the loss landscapes of these systems and see that models that have flatter loss landscapes end up having better generalization performance overall, which is what we hypothesized in the beginning. And of course, correlate these with the ideas of entropy. When you do that at large scales with a lot of different hyperparameters and different optimization methods, what you end up finding is a pretty good correlation between the loss entropy and your ability to extrapolate beyond your training set compared to something that represents the actual error in your extrapolation. So this here is some sort of extrapolation set, one in which you know the exact values at the extrapolation, and this one uses a training set alone, which is really useful for us. We want to be consolidating our metrics with respect to our training set, but not necessarily evaluating your systems only in the training set, which is why this kind of intuition, again, is useful. This has been used in a lot of different places. It's still in molecular simulation. One very interesting example comes from a group of Priya Vashishta at USC, and they have trained a model that's called Allegro over here with some sort of sharpness aware. So during the gradient optimization process, you introduce a loss that is dependent on the entropy of your system, the entropy of your loss function. And by introducing that entropy of the loss function, Just by performing that kind of analysis, you already improved the model from a red to a blue over here. So improving all of these performance metrics in terms of time to failure. So another example, you can take transferable lessons from machine learning, from the machine learning literature, and know that there's a wealth of optimization strategies, including ensembling of weights or really the stochastic weight averaging and so on, that ends up leading to models with flatter loss minima compared to sharper loss minima. And that could be, to you, who are probably a practitioner of neural network, any kind of neural network model, an interesting takeaway, right? If you try to incorporate these things, will the models generalize better or not, just by assuming this kind of thing? There are several papers. One interesting is from Google called Fantastic Generalization Metrics and Where to Find Them. They performed a very large scale analysis on all of these different hyperparameters and metrics of robust generalization. And the thing that they found to be correlated the most with robust generalization is this idea of loss flatness. So interesting takeaway for us to understand here. But in terms of building blocks of AI+Science, and again, going back to what Zach mentioned, and thanks, Zach, for letting me borrow this figure, is this point over here. The idea that we're looking at not only data and not only models, as I mentioned before, but also complementing these models with new hypotheses, with new discoveries and new feedback. And that goes into the idea of active learning. What is really active learning? Going beyond just the process of training a model from an initial data set, you might as well also increase the size of your data set in order to make your model more robust or more generalizable, or perhaps more appropriate to the application of interest. The idea of active learning is fairly simple. You have an initial training set that's labeled. You train a model that could be any kind of model. And through experiments, simulations, you kind of create new data points that are unlabeled. All of these data points are being unlabeled. They required some process of labeling. And this process of labeling requires an oracle, for example, a human annotator. And as you look at this annotation and create new data points, you basically augment your training set. This is the process of really active learning, starting from initial data set, augmenting the data set in a somewhat automatic way. So let's say that you're doing some sort of capture and analysis of whether you're a robot or not. You're, in a sense, doing some sort of augmentation. You are yourself labeling data to train a particular model on whether this is a crosswalk or not. And perhaps by different ensembling methods, you might be able to achieve a good answer on whether, first, whether you're a robot or not, or second, whether the models can be trained with the right labels. So what happens nowadays? You've probably seen interesting examples of captchas that look very crazy, like this one. So as I was preparing this lecture, I received this captcha, and you can immediately see this tiger over here with words like truck, frog, was it more truck, and the cat reverts here. And a lot of different patterns which look like very psychedelic, and all of these different images that seem to be adversarially corrupted. So one of the questions that you can ask yourself now is whether these things, we're generating data to train adversarially robust models for image classifications, right? So as we are labeling these things and they start to become more and more robust, now maybe we're part already of the entire matrix that is generating data for these adversarially robust models. But just to exemplify how all of these different concepts that I'm mentioning here, adversarial hacks, robustness, generating data, and active learning come together in applications that exist and you're using perhaps every day, and we could incorporate them into scientific machine learning as well. The idea is very simple after all. We can just take a certain data set that has a couple of points. We can try to do some Gaussian process regression, some neural network model with some sort of quantification, guess a particular function, assign a certain uncertainty to it, and compare it against the actual true function of your system. Of course, you're going to have an error over here, but the uncertainty will guide you to select new samples. And as you select new samples, you're performing an evaluation against your actual true function and retraining your models in this active learning loop. You can do that for a lot of systems. What I'm going to show here is not the case of this example, but I'm just going to go back to that particular molecule that I showed you in the beginning. And this particular molecule fails in a very simple type of simulation, right? You perform this molecular dynamics simulation, and you can see that it fails catastrophically over here because, of course, we find out that we are going away from the training set. And that's exactly what we always want. We want to go away from the training set in all of these different examples. How can we combine these ideas of active learning, robustness, and machine learning driven simulations? Well, let's look back at the objective of adversarially robust systems. what you can do is, instead of looking at a classifier, now you have a loss that's a loss defined for a particular regressor. In these kinds of molecular simulations, the regressor tries to predict energies and forces, which is what I need to really perform these simulations. So the idea remains the same. We can get a perturbed loss function, we can get energies and forces coming from an active learning loop, and train a model across an entire data set of study and allowed perturbations that I make purposefully into my simulation system. So the idea is how to really generate these perturbed values, and the intuition from the scientific ML perspective is I'm going to maximize my uncertainty. I'm going to create new data points that maximize my uncertainty. And again, I promised that I would come back to this point of maximizing uncertainty to find new data points. In molecular simulation, the uncertainty can come from any sort of flavor. It could come from an entropy, as I mentioned before. In this particular example that we did in 2021, it comes from a committee of neural networks, really an ensemble that really maximizes a certain uncertainty. So the adversarial attack really distorts an input molecular structure or input data point in order to maximize its uncertainty. But of course, because thermodynamics exists and we want to sample not random points, we have to do it in an active learning loop, and that's also sample based on particular values of allowed perturbations. And these allowed perturbations necessarily come from thermodynamics. So what I really mean with this is that if I had a training data that's shown in blue over here and a test data point that's shown in orange, what I want is not to increase the energy just a little bit, I want to increase the energy a little bit, or I want to increase the energy towards points of interest in molecular simulation, but I don't want to diverge in energy and go super far away from my training set. And that is a requirement in a lot of our systems of interest. So you can construct what is called the partition function. It really allows you to sample these things well. And just not to go too much into the details of the thermodynamics and why this is important, it basically says if I'm allowed to explore or exploit the data that I have in principle. So Murat this morning mentioned a couple of algorithms like a greedy algorithm, an epsilon greedy algorithm. And those values of epsilon of exploration versus exploitation really comes into play for a loss function that's contrived in this manner over here. So is it useful? And how does it look like for a toy example? It can look like something like this. So you start with a training data point, training data that's just the the white points over here, okay? And the true underlying function is this. For all purposes, this is not molecular simulation anymore. It's just a true function that you want to predict, and this is the data that you have available. Your first guess about that true underlying function is pretty bad, right? This is called a double well potential because you see a minimum of energy here, another minimum of energy here, separated by a particular barrier. So in the beginning, you have no idea about the barrier or about the second potential, but you force your system to start exploring these new points over and over by maximizing these bright regions of the space. The bright regions are really the adversarial losses or the uncertainty, also weighted by how likely we are to sample these different data points, and that slowly improves our predictions over time. So is it always like this? No. In fact, I created this particular notebook to show you that you can reproduce it yourself and implement the same results yourself if you want. Of course, I created a particular pipeline to do that, so we don't have to reinvent the wheel for everything. But you can start from a loss or an underlying function that we want to learn, like this one, generate some training data for it, as I mentioned before, just like here. And of course, you're always going to look at parameters that you have, for example, parameters that are used to train your loss function, like the weights that you usually set in a loss function for the models. If this is a neural network, it has a dimension 2 of input, like output dimension, number of layers, and so on. All the things that we know and optimize in neural networks, and train this entire system. So I don't usually set a random seed for this because I like to see the surprises and whether the model is going to keep working or not. But indeed, when I replot the whole process, you can see that it automatically sampled new points. New points are not shown here because they're out of bounds of the plotting range, but you can see points that are sampled over here, points that are sampled over here, new points that are sampled everywhere, and your overall final prediction is starting to converge into the things that we actually want. Again, this is an active learning process, right? We know we have an initial guess, and we want to know about new things. And as we do this automatic gathering of new data points, we're also updating our knowledge of the underlying function and getting conversion to better results. In molecular simulation, this is slightly different. I like to show this example just to show what is an adversarial attack for a molecule. If before I was assigning a small perturbation to an image and changing the image, or perhaps indistinguishably changing the image to us, it's also useful for us to understand whether molecules, the case of molecules is the same. And this is the case of a tiny perturbation in a molecule that chemists and material sciences in the room will understand as being apparently small, but also leading to a very high energy because of this bond being compressed. The fact that happens behind the scenes in a model is that you maximize a certain adversarial loss over here by also maximizing the variance of your predictions, and you end up confusing the model to lead it to extrapolation results. So the final energies that are predicted end up being negative, meaning much, much smaller than the actual most stable state of this particular molecule. So that is a wrong prediction. We know that it's a wrong prediction because we know the exact ground state of this particular molecule, but the model does not. So that's why we sample this point, to tell the model that there are other points out there that go beyond this particular system. We can do that for a lot of different cases. We did it for much more complicated systems, such as these materials over here, and try to generate trajectories using a traditional method and using adversarial attacks and getting much better results with say like 1/10 of the data as we initially had, and that allowed us to perform molecular simulations in a much better way compared to what we had before in terms of stability of these simulations. So active learning with these kind of adversarial attacks and these techniques can be quite efficient because basically we're maximizing an uncertainty and we're sampling just a handful of points that we didn't know before. So thus allowing us to go beyond our training set and really augmenting it, without wasting computational resources on things that we already know. So I showed this example to you. You're welcome to reproduce them and have a look at many other systems, and including how to implement them. So if I scroll down, I have an example for molecular systems, but if I abstract away, again, just from the molecular system, and I look at how to implement it in PyTorch, you're going to see that it's not too difficult to understand. Let's go over here to the model, and what we have is we have a system that has as an input species and coordinates, and everything that I need is to set a require grad equals true to really backpropagate my loss with respect to the input structure. And I can do everything that I usually do in the training process of a model. You see, I add a perturbation delta over here that initially is just like a tiny random noise. And I also optimize my model with respect to the perturbation. So really what I'm doing here is I'm optimizing a perturbation with respect to the input system, to the same space of input coordinates, which in my system are Cartesian coordinates for molecules. In the case of image classifiers, they're just pixels, but in your case could be something else. So just to show you that this is all that exists behind the scenes. Of course, you can set up the loss functions to be specific to your systems, and you can set up the alternatives to be specific to your problems, but this is all it takes to generate an adversarial attack, just to show you that all of these concepts are not just abstract conceptual problems that exist in machine learning literature, but also something that can be implemented here. All right, and this concludes our part about robustness of neural networks. Do we have any questions before I just jump into the last part? Other advanced sampling schemes, right? So this other sampling scheme that happens in molecular simulation is some sort of molecular dynamics simulation. So we are comparing it against, say, the traditional molecular dynamics simulation that samples new data points, but it samples with less efficiency compared to our method. There have been works that really explore it based on different types of simulation that really are called enhanced sampling simulation that really drive your system away from what you know. And those tend to be more efficient, obviously. But this kind of adversarial attack is pretty fast to implement, which is why we ended up using it so broadly. Okay, yeah, so these are various concepts, and I just wanted to use the last few minutes to use my soapbox here, of course, and think about how do we use this and how do we connect these problems with applications, right? So the idea in my field is the idea of material science and engineering. We have a lot of different scales that go all the way from electronic structure of materials. Electrons go to atoms, go to grains, dislocations, and sets of atoms at larger scales, and of course go all the way to continuum. So if you're designing new materials, you can think about materials at the continuum scale for like aerospace applications, but whose properties will very often come from the electronic interactions that happen at the atomistic scale. Machine learning for materials prediction often does a pretty good job in making this structure to property connection. This is what we talked about today and many other times. And of course, these inputs between these mappings between inputs and outputs are very generally observed in all kinds of AI+Science. But in material science specifically, what I'm interested in is going beyond what goes into structure and property and also going to performance. Performance is, let's say that I design a new alloy, a new metal, and I want to use it for some sort of application, say a nuclear fission reactor. Do you trust a nuclear fission reactor that has not been tested with a new material over 20 years of operation? I wouldn't trust it. However, are you going to wait 20 years to test a new material in order to build a nuclear fission reaction? Well, we might not have the time to do that. So we really need a very good understanding of macroscopic behavior, lifetime, and of course, uncertainty quantification, which is why I connected all of these things back to the ideas of uncertainty that I mentioned before. I don't want to wait 20 years to test new materials in order to deploy them in practice. We need to understand their performance now. And same thing about synthesis, right? Synthesis is very often about things that are out of equilibrium, things that happen beyond the realms of things that we understand. And so how do we come up with mechanisms to predictive models out of equilibrium theories and really combinatorial spaces that reside in the space of material synthesis? Well, the ways that I do involve thermodynamics. And one of the classical equations of thermodynamics is this. You can get a value of energy that comes over here. This is called enthalpy, actually, but just as a general concept. And this one, which, again, it's entropy. So all of these permeating themes of entropy across materials theory, across thermodynamics, across simulations, they come into play because they're very similar concepts. They all connect with uncertainty quantification, predictive models, and so on. One example. I come from UCLA, and our city of LA is not very well known for the quality of its air. This is an example of a photo from 1954 of the Los Angeles City Hall. And you can see, of course, that there's a lot of smog over here. So one of the advances that have been made in the process of really going away from this and getting pretty good air nowadays. So if you go now to visit us at Westwood, you're going to have pretty good quality air and not this anymore, is the fact that we imposed a lot of regulations, and we as a country and we as states and cities, to prevent the emission of harmful pollutants from, say, diesel engines and car engines, combustion engines in general, into the air. And so these regulations and technologies require not only policy, but also materials developments. And some of these materials are known as catalysts. So Zach mentioned catalysts in his talk here. There are other flavors of catalysts. And these catalysts, interestingly, are very difficult to synthesize. So Murat has a very interesting paper in the past that he mentioned in the beginning of this talk that shows about synthesizability of materials. And synthesizability relates to some value of energy. There is one system that's a very interesting system that's based on silica. This is silicon oxide over here. And that has a range of materials that are metastable, yet synthesizable. Some of these are synthesis driven by out of equilibrium conditions. A lot of them are called zeolites. And zeolites are things that you have used before, even unknowingly, because they're present in laundry detergents. They're present in most heterogeneous catalysts in the world. So everything from the production of plastic to cracking to biomass conversion nowadays, and of course, emission control passes through one of these materials that have only in catalysis 20% value of all catalysts in the world, with trillions of USD in terms of product values, and of course, these more applications that I mentioned before. So the idea of synthesizing materials relates to the idea of recognizing the patterns. So machine learning is pretty good about recognizing the patterns. And so we have to create new computational technologies that recognize the patterns in the synthesis of these structures. For example, there are structures that have particular pores, and these pores are very well fit by certain molecules. And these molecules can work as some sort of lock or a key to particular locks. So just imagine that you had access to all of the space of molecules in the world. You're going to have an infinitely large keychain, and you have to test each one of these keychains into all possible locks that you could have for your own use. This could be intractable for a range of reasons, especially in different timelines, but our interest is really coming up with these relationships in a fast way. So really connecting these molecules and these materials with all of these different concepts of energies, entropies, and so on, using simulations and machine learning to accelerate them. So what you have here is one of the examples that what implemented all of these metrics, that some of which were generated with machine learning, some of which were generated with simulations, that take into account all of these different materials with all of the past literature, with all of the results that we could create in order to design better molecules and synthesize the materials of interest. I'm just going to show you here an interactive visualization as an interesting example that helped us a lot from the machine learning perspective, that having a human in the loop was super valuable in bypassing, say, difficulties of quantifying how good are molecules compared to others. Humans are pretty good at identifying synthesizability of molecules, whereas computers still struggle in a lot of different issues. You can see over here that we selected a particular molecule that had pretty good energy values and metrics overall, and that have been used to synthesize the material. So several of these processes ended up happening. This is just one example of the conversion of the nitrogen oxides over here across different temperature ranges. This is the baseline catalyst that was used. That is typically used in commercial applications. Ours is the green one over here and outperformed these baseline catalysts in both lower and higher temperatures for a range of results and hydrothermal treatments. We did a lot of very interesting things in explaining literature. We explained 60 years of literature of the field, predicted many catalysts with experiments, and predicted the structural features about these catalysts and really deploy them into practice. So that really means that instead of going to a process of trial and error that is typical in material science and going to the lab and experimenting over and over, we can try to accelerate that using simulations, databases, literature, machine learning, and all these human-computer interactions in order to lead us to better results that involve uncertainty, involve entropy, involve a lot of these different examples. So let me just skip here to tell you that this has been performed in a range of other examples. We recently did this for case of electrocatalysts, particularly the case of copper catalysts, and we wanted to study not only a single molecule absorbing on a surface, but several different molecules in different regimes. This is what happens in practice in a lot of electrocatalysts. And we want to evaluate tens of millions of structures without being uncertain about them. So we had to control our extrapolation ability. We had to control our uncertainties in order to explore the combinatorial spaces of all of these electrocatalysts and understand how these molecules interact with all of these surfaces and so on. And of course, we did it for the case of molecular simulations like this as well. In the case of information entropy, you can look at processes like nucleation and growth. So Murat mentioned the case of nucleation and growth, and this is an example of a simulation of copper that ends up moving away from a liquid structure into a solid structure, represented here by these red and green dots. And that can be understood or better modeled using these concepts of entropy, which is not what we typically do in material science nowadays. So hopefully with this very entropic lecture, I was able to convince you of several different cases. Why uncertain quantification is important, how do we implement them for neural networks, why robustness is important, what happens to really cause lack of robustness or improve robustness in neural networks, and how can we use them in a range of different examples and applications. If you go back home and don't remember a lot of things, I hope that you remember at least this, that not all uncertainties are equal. Understanding what is aleatoric and what is uncertain epistemic is super important. There's a lot of room for improvement on that, of course. The case of information entropy is not the only approach that you can take. You might develop your own approaches for your field, especially uncertainties that make sense. And that also is the case for robustness. There's a lot of different ways to improve the robustness of machine learning methods that may be as well the most important challenge that we have to solve in order to deploy machine learning methods for applications that vary from high stakes applications to simple scientific ML. And that can be quite counterintuitive. we showed examples in the case of adversarial attacks. It's not simple for us to get to that picture because we're always understanding them from a very superficial level. Neural networks tend to be quite difficult to probe, but scientific understanding can be our key to really find out how to better extract insights from all of these things. And of course, there's no lack of possibility in the domain of AI plus science, right? Understanding the advantages and disadvantages of these different methods, different uncertainties, assigning the correct values for each one of them is part of science, hopefully with a bit of optimism. And if you're interested in material science, as I am, and very excited about thermodynamics and all of these things, we can talk about that later, but there's a range of possibilities to discover within material science and technologies. And of course, it's a very impactful field. So yeah, with that, it's just, of course, this work is not done alone. There's a lot of colleagues, especially at Lawrence Livermore, helped me consolidate a lot of these things now at UCLA as well. And of course, I'd like to thank you for your attention as well and open for questions.
Questions for Daniel?
Of course. Yeah, so this is the last part, right? I skipped, of course, but the idea is that what is nucleation in rare event is basically something that's not in a training set, right? So essentially what we want to understand is when I perform a simulation within the material science perspective, I want to find out the points that are very rare. And points that are very rare can be something like nucleation of a crystal from a metal, right? So that happens because over here it has 300,000 atoms over 2 nanoseconds using this ramp of temperature over here. And for the longest time, nothing happens until everything happens. And so what is that everything that happens? And when does it actually happen? And why? So this is the idea of uncertainty, right? Going back to the point is finding what is a rare event means finding the point that's distant from the everything else that we have in our training set. And the training set could be just liquid structures. And the test sets and the things that I'm probing can be a solid structure. So finding out the intersection between phase space of liquid and solid is something that we do. Over here, there's a lot of thermodynamic reasons for why the entropy reduces when I go from the liquid to the solid. Obviously, over here, this delta H correlates to heat capacity. So there's a slight discontinuity over here for reasons that we don't have to go in details over here. But of course, detecting the outliers basically correlates to finding out what is this most solid-like structure that we can find in a liquid. And these most solid-like structure is difficult to detect. We cannot do it programmatically in a lot of different examples. Over here, I show examples on what is so-called the classical nucleation theory, something that really relates to how these materials form from the energy perspective. And there are only 2 outliers, B and C. B is due to an artifact in the method that we use. It's a graph theoretical method to detect these things. And C is a very compact, solid-like representation. You can see some order here. So this is the kind of structure that really leads to the formation of a solid in the end and really ends up minimizing the overall energy of the system. So that's the process of detecting an outlier, or really that's the consequence of detecting an outlier, finding out what is the nucleus that really originates that simulation. But in principle, that's just calculating a delta H. The things that I mentioned before, calculating a delta H and really maximizing the surprise that you have about a certain variable or a certain environment or a certain data point is all that we do over here.
Different from just using a traditional physical measure to detect.
It's different. Yeah, it's different. A lot of different methods to detect these examples tend to be tricky. They work well in solid phase, but not very well in liquid phase. And because there's a lot of movement in liquid phase, so to speak, it's very difficult to detect them reliably.
But entropy is also, the matter of entropy you said is also physically deformed and it's from physical properties. To me, it's like they are essentially the same thing.
That's a pretty good point because they're very, very similar, but they're not the same thing. One is information, the other one is thermodynamics. There's a couple of nuances there that I'm not going to go into detail. I'm happy to tell you later about what is the exact difference between them. But information is operating in the data space. Thermodynamic is operating in the entire space of materials with all of these different energetic considerations. So they are they approach the same thing. And I think that's the value of this kind of formulas. One in which you approach a quantity that's hard to compute, thermodynamic entropy, with something that's easy to compute, information entropy over these space of data. Any other question? I think we're,
Yeah, maybe in the interest of time, let's thank Daniel again.
all right, thank you.